Alright, hello ladies and gentlemen. This lesson is going to be on two things, completing the square and the difference of two squares. I'm going to teach you how to generalize in maths, and I'm going to teach you how to recognize the pattern of completing the square and the difference of two squares. These are important. First point, this is in algebra, the general topic of algebra. The opposite of expansion is factorization. So we know that once we've expanded something, we can go back the other way and factorize it, and we should get the same answer again. Secondly, to expand, we use the distributive law, or we can use FOIL. Now, if you can remember, FOIL stands for first, outside, inside, last, and works if we have two pairs of brackets, bracketed terms multiplied together. Maybe something like x plus 1, x plus 2. You use your little FOIL to do that one. First, outside, inside, last. Cool. Lastly, to factorize, we need to know the highest common factor of the terms. So for expanding, we need to know distributive law and FOIL, but to factorize, we need to know the highest common factor of the terms that are there. That is, unless we can recognize some sort of pattern. And I'm going to teach you today two patterns that mathematicians have recognized. So the first one, let's just try a couple of examples. I'm going to start with x plus 1 squared, then go to x plus 2 squared, x plus 3 squared, and then we're going to try a general function where we don't know what this number is, but it could be any number, any integer number. Alright, so x plus 1 squared does also look like this. Remember, if you square anything, you're just multiplying it by itself. So that's what that looks like. And if we use our FOIL, I'm just going to draw my lines up here and down here for now, but I'm not going to do that on the next ones, so you just have to remember that's what happens. So if I multiply the two first terms together, I get x squared. If I multiply the two outside terms together, I get 1x. The two inside terms together, I get 1x. And I times the two last terms together, I get 1 times 1, which is 1. Conveniently, that makes x squared, and I can combine these two like terms together to make 2x plus 1. Cool. X squared plus 2x plus 1. Let's try that again for this second one over here. We've got x plus 2 all squared, which would look like this, squaring both. Then we're going to use FOIL, so multiply those two together, multiply those two together, multiply these two together, and last, 2 times 2 is 4. Combine the like terms, we end up with x squared plus 4x plus 4. Alright, let's do this one. First, outside, inside, last. X squared plus 6x plus 9. Now, if you look at each of these three answers here and where they came from, you might be able to recognize that there's a pattern going on and on and on and on and on. The best way that we can prove that is by using this n letter that I have over here. So let's try it and solve this one, see what happens when we go the whole way. So we've got the x plus n. We're going to solve it exactly the same way that we did before. And you're left with x squared plus nx plus nx plus n squared. Now, the two middle ones are still like terms. We can combine them like this. 2nx plus n squared. And that's very interesting, because what this thing tells us down here is that for any number that we put in for n at the top, it's going to give us this value here. So if we look for a second at this 2n, hopefully, if we look back at each of the tasks that we've done, each of these activities that we've done before, this term, the pronumeral in front of just the x, not the x squared, but in front of the x, should be 2 lots of the number that we started with in the brackets. So if we look over into this one, we've got 6, which happens to be 2 lots of, or 2 times, this 3. If we look back here, the pronumeral is 4, which is 2 lots of the 2 that we started with up here. 2, the pronumeral of x here is 2, and which happens to be 2 times the 1. So we've made a generalization, and it works for those 3 cases. Now this term at the end, sometimes we call this the constant, by the way. You might hear the constant. The one that's right at the end, that doesn't have an x attached to it, is apparently going to be the square of this number that's inside. So n squared, let's have a look at this example over here. We've got 9, which is 3 squared. We've got 4, which is 2 squared. And we have 1, which happens to be 1 squared as well. Cool. So now we know that if we are given any sort of problem, it could be even this. We can actually jump to the end, straight to the end, because we know the rule. We know that x squared, we know that this expands to be x squared plus 2n plus n squared. Now, 2 times our n is 2 lots of 12, which happens to be 24. And n squared, well, what's 12 squared? Can you remember your last times table? It happens to be 144. So we could skip a lot of the working out just by remembering this nice little law called the completing the square law. Now, I haven't been completely truthful. Completing the square isn't going and expanding something. Completing the square is useful because now we know that if we are given in a question, like a test question, for example, we are given this answer down the bottom here that I've written out, and it asks you to factorize it, then we know how to jump back to here because we can recognize what these numbers here are. So, quick test for you. I'm going to erase this stuff down here. If I am given this problem, x squared plus 26x plus 169, could you figure out what the brackets should look like? Something squared. And then try this one. We've got x squared plus, let's go with 10x plus 25. Do you think you could figure out what should go inside here? I'll give you a minute, pause the video if you think you can work it out. The answer is in fact x squared plus 13 and x squared, sorry, not x squared, just x plus 5. Alright, this video has gone much longer than I intended, so I'm going to split this into 2 and we're going to do difference of 2 squares in a second video. Alright, see ya.